Good, we made it. So it's a pleasure to be here. I would also like to thank the organizer for giving me the chance to give this talk. So there is a big change of topic. I hope you can deal with it. It was a fascinating talk, and I'm still busy thinking about all the insight you gave us. So now we have to move to something else. And to introduce you to the something else, I would like to first tell you a few words about the kind of research we carried out in our lab. And this is very much in line with the neuromorphic engineering approach that Giacomo Indiveri introduced in the morning. So our main research is in the domain of fundamental research. We are trying to understand how the brain works by doing emulation of neural function. Again, the same way Giacomo described this morning. We do this with full custom CMOS systems. We use subthreshold analog, asynchronous digital. And in the last decade or so, we have been working into merging CMOS technology with memoristive devices. So therefore, building hybrid memoristive CMOS systems. Giacomo already mentioned that this is a very expensive approach, both in terms of person months, in terms of money, and so on. So whenever we have a new idea, we don't go straight to this kind of approach, but we first use tools as digital processors for fast prototyping of ideas. So in this case, we do what we call simulation of neural networks, and this is, if you want, a conservative approach. What do we do with all of this? We have two streams of research. One is about systems and theory for brain-inspired computation. The other one is about sensing and actuation. And today I'm going to focus on the second one. And because of that, I want you to think for a few seconds about the five senses and about the fact that information that we acquire with our senses is strongly based on spatiotemporal patterns. So whenever we perceive something, there is a lot of information carried by the spatiotemporal pattern of the signal that we are sensing. Because of that, in my group, we decided to design a special computational primitive that we call time difference encoder. A small disclaimer. This is inspired by biology, but it's often representing like many neurons, or even the sensing together with neurons. We rarely try to find the neural correlate of this model into a single neuron, despite the fact that if you saw the talk of this morning by Jota, there are things that we could use of this model to also look into a way of implementing dendritic computation. But that's not the topic of today. Today, I'm going to focus on the application of this module to vision. And first of all, I want to tell you what this is about. So let me take the pointer here. So imagine that you have a synapse and a neuron. A neuron could be a leaky integrate and fire. You've already heard about this kind of model. And we have two channels that are connected to the input of this module. One channel is not producing an output of the synapse, and the other one is. And because we work with biologically inspired computational modules, everything is spiking. So that's why the representation of the two channels is these two horizontal lines, where you see these small vertical lines representing spikes. So what we do is that whenever there is a spike on this particular channel, we sample time. This is represented by the fact that you could have a variable in which you add a given value. We do everything in CMOS as well, so in that case, it means we put charge on a capacitor. And then we let the variable decay over time. And then what happens if a spike takes place in the other channel is that we sample the value of our variable, and we use it as a gain for the production of current to the soma. So if we look again in more detail, we have now the first channel and the second channel again. This is our gain. And because of the arrival of the second spike, we produce a so-called excitatory postsynaptic current. This current is integrated into a neuron, and this neuron is producing a given number of spikes. Now, if I make the time interval between the two events much longer, by the time the second spike arrives, the gain is much smaller. There is still a current, but the current is very small. This leads to integration in the soma, but not enough to produce spikes, and then I don't see an output. And of course, this is a directional element. If the first spike arrives on the second channel, the gain is still 0, so I get no output at all. So now I can repeat this kind of experiment with many different delta t, the distance in time between the two events, and count the spike at every experiment. So now the number of spikes is what I'm representing on the y-axis of this plot. And on the x-axis, I have the delta t, the difference in time between the two events. So now you can see that I have a very nice encoding of the delta t given by the number of spikes. And then now I want to show you one of the many examples in which we put this computational module at use. And I also want to give you an overview of the kind of approach that we use while we do this. And this is something that I would like to call from neural to artificial system and back again. I started by telling you that we want to understand how the brain works, and we do it by building artificial system of the kind that I shortly described before. We can pick one example. Fruit fly can perform very complex flight maneuvers. And they do that by using visual input. So they decide where to go by using visual input. So we like to look at a specific animal, in this case a small insect, and we like to focus on a specific task that the animal can do very well, for which we believe nature evolved optimal solutions given the small size of the brain. So by doing that, we are constructing then physical system, in this case a small robot, so apologize for not flying, but that would be the next step of the work, in which we try to understand how this is done in biology. We port this understanding into a model, and then because we have a physical system, we can test these now behaving agents and look at the behavior of the agents and compare them with the behavior of the biological system and make hypotheses of what is the neural substrate of this behavior. So this is an example of a behavior that I show you later. OK, so let's start and go deeper into the topic. Let's start with obstacle avoidance. Of course, if you want to navigate into an environment, the first thing you have to make sure is that you're going to avoid obstacles. Otherwise, that could create damage to the system, whatever the system is, either biological or artificial. You should all be aware that if you're sitting on a train and there is something very close to the train track, this something is going to move very fast in your visual field, while the hills and the houses far away will move very slowly in your visual field. This is a very well-known mechanism used by insects to safely navigate the environment. So insects are able to identify good direction of motion by using the information carried by the motion flow. So now if you think back about our TDE, and you imagine that the two input channels are now 2 pixels of a camera, the time of flight of an object between the one pixel and the other will give you information about the motion flow. So the faster the objects are moving, the shorter the time between the two events, which means wherever you have high motion flow, you're going to have high activation of the TDEs. And wherever you have low motion flow, you're going to have low activity. So what we can do is to build a network that is representing the visual field of the robot in terms of motion flow. And then what we need to do at that point is simply look for the region in the space with less motion, which will be the region in the space with less activity from the TDEs. So low motion will be low activity because it's a long TDE, a long time difference, sorry. So we built such a system, and we put it in a robot. And I'm going to show you how the robot behaves in, for example, an experiment that is typically run with insects as well. And the behavior that is observed in insect is corridor centering. So insects are flying in a wind tunnel, and what people have observed is that they tend to stay in the center. And the narrower the corridor, the more they tend to stay in the center. But also we can then play this autonomous agent in a more natural environment and see how it navigates in the world. So I didn't give you a lot of details on how we did it, but believe it, it's spiking from the sensor to the actuator. The sensor itself is spiking, and we have an end-to-end system that is driving the motor in an autonomous way. Then, of course, we want to fully characterize behaviors, such the one I just showed you. So, for example, we run many repetitions of the same experiment in different conditions, in this case, a narrow corridor and a wider corridor, so that we can later compare with biological behavior. But as you might know, this kind of experimentation is very time-consuming, and it's also a challenge to produce very different environment in which you can run your robot. So what we do is to move from a physical system, which is for us very important because we don't want to have the reality gap, so we need to have the physical system first. But then to get more data and more complex behavior from our agent, we absolutely need to move to a simulated environment, and that's what you see here. So you have an arena in this example with a few obstacles, the blue squares, while the red trajectory is the trajectory of the robot moving randomly within this arena. And we look at the behavior for a different amount of clutter in the environment of the robot. And you see that if there is a lot of free space, the robot is just going to explore the space. If there is more clutter, the robot is going to identify corridors and move through these corridors. If the clutter is too much, the robot is clearly going to be stuck. But now, of course, you also want to put intention in this movement, in this behavior. So you start thinking, okay, but what if I want the robot to go to a specific place? How do I put this intention? And how do I make sure that the robot never loses the reference in terms of its location and orientation in the space? So now you start talking about navigation. And also there we took inspiration from biology, and we went into the topic of polarization vision, because again, it's very well known that insects use the polarization of the sunlight to orient themselves in the world. So this is also done in a simulated environment, and here you have a polarization simulated camera, which we divided in 4 receptive fields, if you want, and for every receptive field, we have 3 kind of polarization filters represented by the 3 colors. So this would be an image at looking at the sky and looking at the polarization produced by the sun in the sky. And this would be the response of the 3 different receptors that we are simulating in our system. And so now, of course, you're going to have, with this receptor, a representation of the polarization in the sky, which should give you information about your orientation in the space, except that, as you can see, just by the stimulus itself, there is a 180 degrees confusion. I'm missing a word. I'll find it later. Anyway, you see that if you look at every filter, you have this repetition of activity every 180 degrees, and you have it for all the filters, but by having this collection of response, you can figure out the location in space, and that's what you see here. So here we have time on the x-axis and neuron ID for the black dots. This is a so-called raster plot in which we look at the activity of now a polarization network that is expressing the polarization perceived by our receptor. And in red, you see the measured angle in degree of our robot while navigating into a clutter environment. So ambiguity was the word I was looking for. The robot, in this case, the network gives you two possible representations with the 180 degrees ambiguity, but of course you need to solve this. And again, looking at biology, there is a structure in the brain of the insect called central complex, where different sensory cues are brought together to get a very robust representation of the world. So that's what we did here. This is our small model of the central complex. The polarization network is producing spikes because of the activity of the receptors. And imagine that you could drive the central complex with proprioception. So you're moving around, which means you're turning your wheels in case of the robot, so you have an understanding of the kind of rotation that you are producing in the environment, within the environment, and then this can help you solve the ambiguity. So now you have the activity of the central complex, which is very well superimposed with the angle in space. So we have done obstacle avoidance. We have found a way to figure out where we are going. We want to put the things together, and that means that we have to put together the building blocks that we are prepared. So what I told you about already is the optic flow kind of obstacle avoidance that is represented in this part of this network. And then I told you about the generation of a compass. So the central complex is, in this case, our compass, thanks to information about polarization of light. And now you have to imagine that I have a desired direction, and I need to figure out, where should I move such that I can go in that direction. But of course, the outcome of this error estimation, if you like, shouldn't drive directly the motor, because priority should be given to obstacle avoidance. That's why between the delta direction and the actuation, we have the optic flow obstacle avoidance algorithm. So how do we do the delta estimation? So estimating the error. We always look at biology, so it's probably boring by now. Whenever we have a question, we ask biology for an answer. And in this case, often insects. And also here, we get inspiration from the fact that it has been observed that vectorial computation of orientations can be performed within the brain of the insect. And that's how we implemented it in our network. So imagine that we want to have a simple output motor command. So we have 4 populations. One for saying the robot, you should keep going forward because you're doing all right. My error is very slow, it's very small, so keep on doing what you have been doing so far. Or you should go left because that's where your destination is. You should go right, or you are totally off, so make a U-turn. To activate this population, you want to make use of your desired direction, which is in this case represented by a bump of activation in a ring of neurons. And also, the same way, you want to make use of your current direction, which is another bump of activation in a ring of neurons. That's the central complex I showed you before. And so what we do is that we connect this kind of activity in an excitatory way in those 4 populations, but every time we do a 90-degree shift. So we have 4 different orientations for these copies. And the desired direction is represented into this population through inhibitory connections. So the desired direction is a negative. So that's why that's how we're doing the error estimation. We are subtracting 2 things. And as you can see, in this case, in which the current and the desired orientation are coinciding, so I should keep on doing what I'm doing. And I look at the difference, which is now the blue activation. So the blue represent the activity of the neurons that are computing these differences. And you see that the highest activity is visible in the forward population. So correctly, this very small neural network is able to decide I should go forward because I'm already going into the right direction. And then we put everything together. And again, we look at the behavior. Again, we have an arena with obstacles, and we modulate the clutterness of the environment. And again, we see that the robot is able to navigate within this environment and to go in the direction that was programmed in the system. So in this case, the desired direction was this one. In this case, was this one, and so on. And now we're also showing the understanding of the orientation in the environment that the robot has by means of the activation of this population, and superimpose again, we have the angle. And you see also, if you like, that there are challenging situations. So now, in this case, the robot is turning a lot. So it's much more difficult to keep all the cues together to have a unified representation that match the angle very well. So you start seeing that this is a challenging situation for the robot, and the robot might lose track of its orientation in space. So let's go back to the topic from neural to artificial systems and back again. I tried to show you piece by piece how we put together this network. And now I want to give you the example of only 2 behaviors that we looked at and that we can compare to biology. We looked at many more, but I had to pick one because of the limited time available. So one of them is something that we call risk-taking, but it is also related to the understanding of body size. I told you that by doing obstacle avoidance, our system is looking for the region of space with less motion flow. Or you could say it's avoiding the region of space with a lot of motion flow. And we do that by inhibiting a winner-take-all network. So if you do a one-to-one inhibition, you're only going to tell the agent, don't go to that precise place. But you could decide to spread inhibition and say, OK, you should avoid much more. The obstacle is there, but to be safe, avoid more. And that's what you see here. So we have a parameter here, which is 0, 2, and 4, and that's the spread of the excitation. So you see that if there is no spread of excitation, the robot is really able to engage into navigation in a narrow corridor, while this is not possible at all for the yellow agent that has a much wider spreading. So you could put together these 2 concepts, and body size, you want it to be fixed as much as possible, but you could decide, OK, I'm on the safe side, and on average, I avoid areas, I avoid entering gaps that are bigger, that are smaller than twice my body size. But now, if between me and a gap, there is a very nice odor coming through, and I can smell food, maybe I'm willing to compromise and get some more risk-taking behaviors so that I can reach the food source. And another, a bit more complex behavior that can be directly compared to the biological one, it's related to entering a gap. And so biological experiments have been performed with insects where they are in an arena where there are 2 gaps, and one is bigger and the other is smaller. So what you see here is the behavior of the robot in such an arena. And what you see here is the repetition of these experiments. So here you have the gap size of one of the gaps, and the other one is kept fixed at 10. So we start with a very small gap for the one we are evaluating here. And at some point, we get to a gap size that is comparable to the other one. And what we observe, in analogy to what has been observed in biology, is that if one gap is much smaller than the other, the insect is going to prefer the bigger gap. And that's represented here by the fact that the entering probability in the small gap is very small. But then as soon as the 2 sizes are comparable, you get to a 50% probability. And then if one becomes bigger, and again, you have to relate all of this to body size, eventually it doesn't matter anymore that one is bigger. If they are both big enough, you would go with the 50-50%. OK, let me use the last minutes to conclude. A complex system with animal-alike behavior can emerge by combining local neural units in a bio-inspired architecture. We build each block and then we put them together, and we can observe complex behavior. We implemented this architecture in a distributed, parallel, and asynchronous neural system, robustly performing biologically relevant tasks in closed-loop experiments. It's an end-to-end system. It's spiking. It's neuromorphic from the sensing to the motor commands. Very interesting concept that I didn't touch so far. Once hyperparameters are tuned to achieve the side behaviors of the local units, not of the agent, different tasks can be performed in a variety of environments with the same single set of parameters. So in that respect, we can say we identified a robust computational principle. This research leads to reasonable hypotheses and prediction that can be validated with neuroscience experiments. So I hope this closed the story of from neural to artificial systems and back again. And I would like to acknowledge the people involved in this work, most of all Torben Schope, which was the PhD student doing most of the work that I presented today. And of course, thank you for your attention. And I'm happy to take questions.
Thank you, Elisabetta. I thought it was very interesting. I'm not from the field, and I thought it was fascinating. I hope you liked it too, and I hope you have some questions for Elisabetta. We have some microphones there, so please just feel free to stand up and just go there and ask a question. And don't be shy. If not, I'm just gonna... Oh, there we go. We have a volunteer.
Thank you very much, Elisabetta. That is fascinating. Maybe I missed it, but I understood the temporal difference calculation and how this can be used to essentially detect important information, let's say, for the agent. How does the agent learn? I think I missed the learning part.
You miss it because it's not there. Okay. So this system is as simple as possible, and it has been engineered by a human expert. So the intelligence was in the human expert, and there was no learning. So we work a lot on learning as well. But here we look at stereotyped architecture in the insect brain, and most of them are determined genetically. So they are not even learned in the brain of the insect. But we do work on learning as well, and ideally, in the long run, you would like to put the two things together.
Thank you. Next question, I see there.
Yeah, so thank you. That's really fascinating what you can do with these relatively simple means, right? I found your comment about the hyperparameter optimization towards the end quite intriguing. So it sounds to me like if you haven't carefully tuned the hyperparameters, this generalizability is limited, if I understood correctly. And if you tune them, then it actually generalizes quite nicely. Is that accurate? And related to this, what did you actually use for hyperparameter optimization there?
I guess the brain, I don't see him, but maybe the hyperparameter optimizer is sitting in this room, which is a limiting factor, if you like. So we are now moving more to automatic tools for doing that. But to go back to the original question, the interesting aspect to me is that we tune the parameter to do a simple task, like, for example, avoid region of high optic flow. Mm-hmm. We don't tune anything about the behavior. Mm-hmm. So every building block, we know exactly what the building block has to do, mm-hmm. and we put it in there. We engineer it ourselves. And then the generalization that you are talking about, I would see it at the behavior level, mm-hmm. because then we are able to put this robot in many different contexts, mm-hmm. and we don't change anything. So the generalization, if you want, is in the behavior. There is a winner-take-all network. There is our general-purpose computational primitive, if you want, that is used in many different places. And I'm not sure I answered your question, but I'm looking forward to talk to you in the breaks, because I think we have plenty of input for discussion.
Indeed, very interesting. Thank you very much.
Thank you.
Thank you. I see there's one more question. Great, thank you.
Yeah, exactly. Thank you very much for the inspiring talk. Leon Batk, mein Name, from University of Münster. And I wonder how distance is incorporated into this model, since we mainly talked, or you mainly talked about heading or heading errors, current heading, etc. But yeah, so why or how is distance incorporated to determine, let's say, or is there a way to determine an absolute position in space, or kind of is there any mapping capabilities in the model? Thank you.
Very interesting question. In this particular model, we didn't have any explicit estimation of distance. Everything was relative. If there is more motion, it's closer. If there is less motion, it's more far away. And we didn't need to estimate the distance. Torben Schoppe, by now, moved to this very same country and city where we are now, and he has been continuing this work. So his most recent work in this domain is exactly about estimating distances, and this is unpublished work, but he could already achieve results in which he achieves to do a distance estimation using the same principle and exploring more of this basic understanding that we did so far.
Okay.
So it's getting there.
Yeah, thank you very much.
You're welcome.
Thank you. Are there any more questions for Elisabetta? If not, thanks Elisabetta again. Please thank her. Thank you.